It's time for some more Veritasium. Specifically, the biggest misconception about football. Okay, what? Stability? You can say the same thing about nuclear engineering. For those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry. From engineering to operations to emergency response. I don't think to know everything there is nuclear, but I can certainly share some knowledge. Let's see.
This is Tom Brady. He's the greatest American football quarterback of all time.
I'm not sure I'm qualified to weigh in on that, but I'm going to go ahead and assume that's controversial.
Holy shit.
Can you hear it go by you?
Yeah, it's scary.
He's won 7 Super Bowls and has thrown the most touchdown passes in history.
Oh, that one hurt the chest. I heard that.
Right in the chest.
I'm like glad I'm not catching those.
Every quarterback takes pride in their ability to throw a tight spiral. The tighter the spiral you throw means the more control you have of the football.
I mean, sure, spinning's going to add angular momentum, and it's going to stabilize the football's orientation through gyroscopic stiffness. So it'll be more resistant to random aerodynamic torques. You're adding more control mechanisms in that resistance to, say, the wind. Reduces drag, maintains nose forward orientation. Kind of like launching a neutron beam through a very well collimated guide tube. You've added angular stabilization, but doesn't necessarily mean more accurate. I know that's not what Tom's saying. His accuracy is going to depend more on the initial vector, aligning with the target, your receiver.
He analyzed his throw in detail.
Have people shot you in really slow motion for the release and everything?
Never.
And discovered something surprising. Even Tom Brady can't throw a perfect spiral.
Well, a perfect spiral is an ideal case. No one can. Just because he's arguably one of the best quarterbacks ever doesn't make it perfect. Then again, perfection's highly overrated anyway. And I'm sure perfect spiral would involve somehow throwing it in a vacuum, which is going to ruin your day because you're in a vacuum. Just like it's hard to design a perfectly spherical nuclear reactor. It's just not practical for similar reasons.
Look,
Said hut.
on his deep passes, no matter how hard he tries to spin the ball cleanly around its long axis, if you look closely enough, you'll notice this little wobble. Not only that, there's a slight drift to the ball, which means even Tom Brady
Makes it effective for practical purposes.
can't throw straight. Virtually all his long passes curve to the right.
Well, again, that's just a virtue of being in the Earth's atmosphere. Goes back to how no reactor core is perfectly symmetrical. You can change the enrichment so that it's more symmetrical. Like, not all fuel assemblies are the same enrichment, but it's always going to be a little off.
But these aren't mistakes. They're actually fundamental to the physics of throwing
It's
a
not a bug, it's a feature. And yeah, it's fundamental to how we live on Earth.
football accurately. To find out why, we ran a full computational fluid dynamics analysis,
Nice.
tested spinning balls in a wind tunnel, and even embedded sensors in real footballs.
That's crazy.
Now, admittedly, who are we to tell Tom Brady anything about football?
I've never really...
Could talk about the physics of it, but I mean, at this point, it's a difference between an engineer or a physicist talking about a really, really good reactor operator in this case. You can certainly talk about it, but without necessarily insulting your really good reactor operator, telling him how to do his job. It's just a different way of looking at things.
play much football. I grew up in Canada. I'd be much happier to be playing hockey. Like, why can't I throw at all? That is so rough. Okay, well, he'll walk you through it. I'm not gonna bother doing it. Yeah.
Try to do this. Over-exaggerate the tilt. So instead of standing straight up,
Lean forward.
lean like you're almost like a shortstop, right?
Yeah.
And like you're falling over,
Yeah.
and then you're just here.
Baseball analogies in your football video with physics and science and nuclear engineering insight. I love it.
Like that.
Good catch.
So
good
lean
catch.
over a little bit.
Like not ready for
So
it.
get down like a shortstop.
Yeah,
Even
like
more.
this. Even more?
Yeah. Now
Yeah.
throw it sidearm.
I feel like this is weird.
There you
This
go.
is
That was a better
stability.
throw.
That is a better throw.
It was really good.
What's the key to throwing like a really tight spiral?
The key to me is, first of all, you got to have very light grip pressure on the football. I learned over a period of time that I had to be really efficient with my mechanics. I had to have all my energy going right toward the target with a very relaxed posture. And then it's a really smooth, efficient throwing motion.
I mean, that's just it. If you stiffen up or cause too much wobble, it's just going to be a much less efficient process. Less of the energy is going to be going forward. Now, it's easy to say that. Actually doing it's going to take a lot of practice.
And then how are you actually imparting the spin to the ball?
So you're really popping your wrist at the end. So I can even go really slow and just pop my wrist at the end. And even that little bit of wrist pop will create a little snap on the ball as it releases from my fingertips. Henry, you can't drop the easy one.
That's
Cool that he got Tom Brady to be on his show. That's got to be fun.
snap and the spin it creates is the key to Brady's record-breaking throw. But the big question is, why? I mean, what does the spin actually do to the football?
Stabilizes it. It's the same reason why control rods have guide tubes, because you want them to be inserted in just the right spot so they affect the reactor in the right way. Some of them even have helical vanes or even twisted flow baffles to promote more efficient coolant mixing. It's all about heat and flow profiles.
It seems like such a simple question, but the physics turned out to be much more complicated than I initially thought. In fact, physicists...
It's a simple concept, but the math and trying to get it optimized and dial it in, yeah, it adds up.
Studying the problem didn't get close to the real answer until just 5 years ago. So let's break it down from the start.
A question for Tom is, can he throw the ball without spinning it?
Like a knuckleball?
Yeah, can you knuckleball a football?
Yeah, I could try.
That's gonna have a little bit, but you can, yeah, I guess you could try.
Can I throw it underhand?
Yeah, however you want to toss it. Even overhand, there's no way to do it without getting a spin on it, or it's just gonna mess with you?
I mean, have to almost throw it sideways.
Yeah.
Sideways football.
No, that spun a little bit.
When you launch a ball without spin, perfectly aligned with the direction of motion, it seems like the air flowing over the ball will be totally symmetric. But this is unstable. Any slight disturbance, like a tiny bit of wind, will cause more air to hit one side than the other. And that starts to change the ball's orientation. And now, more area on that side is exposed to the oncoming air, so it deflects even more. So drag on the ball increases, it's pushed off course, and it can begin to tumble.
The total drag force on the ball is proportional to the area presented to the airflow and the drag coefficient. That's just a measure of how streamlined an object is. Pointed straight in the direction of motion, a football is pretty streamlined with a drag coefficient of just 0.14.
I mean, that's pretty good. Give you a sense a car is going to be 0.3, 0.4 range.
That's better than a bullet. But on its side, the drag coefficient is 0.85, which is worse than a cow.
Man, I'm learning a lot today. That's what I'm going to use with all the quarterbacks going, man, your drag coefficient sucks. What are we doing? We need 0.14, 0.85, no good.
To make matters worse, when a football is going sideways, it exposes nearly 70% more area to the oncoming air. And
it's all a surface area thing. It's the same way that neutron flux works, is it's neutrons flowing per unit area. And that's going to translate to radiation dose per unit area, heat per unit area. And that's why there's so many intense calculations into an optimal heat transfer profile for the core to keep going.
Combined with the higher drag coefficient, this means that the drag force is 10 times greater than when the football is aligned with the throw.
So an unspinning ball can end up going sideways, meaning it decelerates up to 10 times faster. Plus, as it tumbles, the air pushes on it in different directions, making it move unpredictably. Now, in some cases, you actually want this.
Like when kicking the ball back to the other team, punters sometimes intentionally kick the ball end over end so that it gets pushed around erratically. That makes it far harder for the opposing team to predict where the ball's going to go and get under it. But when you're passing to your own team, you want the ball to be predictable and go as fast and as far as possible. And for that, you need spin. The benefits of spin really became clear in the mid-1800s during the Crimean War.
Rifling?
Back then, soldiers were armed with muskets that fired round lead balls. And to make reloading faster,
try making little football-shaped rounds.
On the battlefield, these musket balls were made significantly smaller than the barrel. But when the gunpowder
Mario
was
sound
ignited,
effects.
some of the expanding gases would then escape around the bullet, making the bullet's exit velocity
gonna bounce.
unpredictable.
Yeah.
This, combined with inconsistent manufacturing and the round ball's poor aerodynamics, meant that muskets were somewhat unreliable.
There was a British
Don't want them to blow up in
Army
your face.
musketry instructor
nice.
who famously said, "I'm willing to
We're adding historic weaponry into this.
stand and be shot at all day long as whoever's shooting at me with the smoothbore musket promises to aim at me every single time," because he knew the bullet's never actually going to go where the gun is being aimed.
All of that changed in the fall of 1854. Russian troops huddled in Sevastopol under siege by French and British forces. The soldiers watched as British troops set up on a distant hillside. They were far out of standard musket range, so the Russians weren't worried. When suddenly, a window shatters.
They were shooting through the windows of the Russian barracks at their naval base in Sevastopol, 900 yards away. They're shooting bullets through the windows.
But these were no ordinary bullets. 8 years earlier, an enterprising French army officer, Claude Etienne Minier, made a breakthrough. He developed a conical bullet with a hollow base and an iron plug that would fit into it. So when fired, the gas pressure drove the plug into the base, which expanded the bullet, pressing it firmly against the barrel walls, so no gas could escape. This made the bullet's muzzle velocity much more predictable. But it also enabled something else. The expanded bullet could grip spiral grooves carved into the inside of the barrel, called rifling. This imparted spin to the bullet as it shot out. And this is key, because all spinning objects have a fundamental quantity they can serve: angular momentum.
Yep. Non-spinning bullet is a bit like trying to fire a nuclear fuel pellet into a moderator pool with no cladding. It's just going to tumble, wobble, and probably hit your boron plate. But this is going to essentially smoothen it, and it behaves like a well-moderated, steady-state power profile, which is what you want.
This helps them resist changes in their orientation.
It's just like the spinning top. Now, without spin, the top just falls over like you'd expect. But if we add a little bit of spin, we can see that it resists changes in its orientation. So if I give it a little touch, it reorients itself in the direction of its angular momentum.
Yep.
A similar thing happens with a spinning bullet. Its angular momentum resists changes to its axis of rotation. So even if wind applies an unbalanced force to the bullet, it maintains its orientation. This reduces drag and helps the projectile fly further, faster, and more accurately. The exact same thing is going on when Tom Brady throws a tight spiral.
The important part of a spiral is you feel the wind blowing at us. If the ball wobbles at all, it's going to catch a lot of resistance in the wind, and it's going to slow the velocity of the ball down a lot and the accuracy. The tighter the spiral and the more it spins, the more it can just rotate through the air, and the wind will have a less effect on the ball. So for any good quarterback, the ability to throw a tight spiral is really important when you play in windy conditions.
A spinning ball will maintain its
That's true, emphasizing the windy conditions part.
and therefore cut through the air with a smaller frontal area and a lower drag coefficient. This all makes sense, but here's where things get weird. If the ball is maintaining its orientation, then on a long Hail Mary pass, it should stay pitched up like this the whole time, just like when it was thrown.
Well, that's just due to aerodynamics. It's going to impart a torque on the football and cause it to flip. There are similar feedback effects in nuclear power plant, such as xenon oscillations, which is one of the things that reactor operators have to deal with, and one of the reasons why it's a pain when operating a nuclear power plant in a load-follow situation where you're constantly changing power level. Because xenon 135 is a reactor poison. It's actually better at absorbing neutrons than control rods, but it's an unfortunate byproduct that is produced from fission. Now, if you're at steady state, well, so is the levels of xenon 135, so it doesn't really do anything. However, if you do a down power, xenon is going to spike because suddenly there's less fissionings which burn out the xenon. And by burn out, I mean xenon 135 absorbs and becomes xenon 136, which is inert, does not have the same neutron absorbing properties. So the point is, it's a dynamic system with natural feedback mechanisms, just like aerodynamics.
That is not what happens. There's kind of a paradox in football, which is when you release the ball, you're angled, say, positive 30 degrees.
Okay.
And when your receiver catches it, it's angled negative 30 degrees.
Perfect. I love that.
Gravity.
So what we just said was angular momentum makes the ball hard to pivot.
Okay.
But what we saw was it pitches from this to this in 4 seconds. So
What is it? Turnover.
Yes.
Is what we would call
exactly.
that.
Now,
Not to be confused with turning over as in turning the ball over to the other team. That's what happens when someone on the other team intercepts it.
Turnover is essential to a good throw because it means at every
That is just so ironic. Saying something like turnover is essential because turnovers are what you want to avoid. I know one important statistic in football is the turnover ratio in terms of how often you give up. Like a team having a positive turnover ratio, that means they took the football from the other team, whether it be an interception, a fumble, or whatever, have something like a 70% or higher, depending on if it's NFL football versus college football or whatever, chance of winning on the other team. And that is not trivial at all when you play enough games. I've taken a few statistics in sports classes as some electives, which were a lot of fun.
point along the arc, the ball's orientation
Different type of
stays
turnover
closely
here, though.
aligned with its direction of motion. That means it stays pointed directly into the airflow, which minimizes drag.
Now sure, you might think this isn't that crazy. I mean, arrows and birdies align themselves along the path of the arc as well. But
that kind of birdie.
that
Sure.
works in these cases because the objects are front-weighted. The feathers catch the air and get pushed behind the heavier tip, which leads the way. But football is totally different. I mean, it doesn't have feathers or fins, and its weight is evenly distributed along its axis. So it just can't use the same mechanisms to align itself.
So in 2020, the editor-in-chief of the American Journal of Physics decided to figure it out.
Really?
I was surprised at how many bad explanations that were easy to debunk got published. When
Wow.
you think about it,
I like
it
this
doesn't
guy.
make any sense because the air resistance pushed the nose of the football up. And you want the nose of the football to go down. So it's pretty curious.
So Price put together a theoretical model
It's not a bug, it's a feature.
to explain the football's turnover. And today, we're going to see whether his findings hold up by simulating Tom Brady's own throws in a wind tunnel.
The idea
Wind
of
tunnel
having
testing is fun.
anything to do with Tom Brady, whom I greatly respect, not only because of his skill, but because of his work ethic. It's otherworldly.
We have these sensors in these balls, so we should be able to see how fast the balls are actually going from inside the ball.
And just to be sure, I'm measuring the speed of these balls the old-fashioned way. A decision I might regret.
Do you want to go right on the side of the dummy with the gun? I'll throw
Okay, so radar gun.
over your head. I won't hit you, trust me. Yeah, right there, perfect. You ready?
Yep.
You know what? I like this playful side of Tom Brady.
45.
Maybe scoot just a smidge more that way. Perfect.
He's getting in his fighting stance here.
Holy sh! 46. You can do another one?
Yeah.
$49.
There you go.
God, that's scary. That's like 80 kilometers an hour. But would you actually use that speed in a game?
That'd be a good speed. That's a normal pass.
That's like terrifying.
Oh, that's funny.
And that's just for a regular throw. For his long throws, the speed jumps even higher, over 60 miles per hour. That's
Love those subtle references. That's only 50% of my power level.
almost 100 kilometers per hour. Now, I'm not about to step in front of that cannon.
I was not built for being an athlete.
You're built for analyzing the.
That's right. I'm here for the data.
And that's why I've got Henry here.
Doing great.
When Tom Brady is throwing, you gotta react fast.
Have people shot you in really slow motion for the release and everything? Did you ever watch that back?
Never.
You guys ready?
I'm ready.
Let's see.
2, 1.
Oh my God! Are you good? You good, Ricky?
Yeah, I'm good.
Oh,
I'm
bring
good.
something?
Is that plexi or is that real glass?
It's plexiglass.
Yeah, it looks
That's
like
incredible.
plastic. Still.
There, you get one shot at these
Oh,
things.
all right, I'd have given it my best. Should we try one more even if the camera breaks?
I don't see the cracks. Wow. So we can go again.
Let's try
Are
one
you
more. Let
kidding
me
me?
just throw a little
All right,
harder.
let's
Glad
go
you had
again.
I'm gonna throw a little.
Glad you had the cover up there.
Now we're broken.
That went
Knock the camera out of his hand. Yep.
Are we able to watch the throw
On
back?
target.
Good spiral. Oh, that's so cool.
The sensors show Brady's maximum spin rate on this day was 628 revolutions per minute. So, armed with this data, let's analyze
Just a
Brady's
shock.
throws in a wind tunnel.
How much data are you used to getting?
0.
Really?
When I played,
Yeah.
none of it was available.
So this is the low-speed wind
cool.
tunnel here at the university. This wind tunnel facility can get up to about Mach 0.2, so 20% of the speed of sound.
Typically, this wind tunnel is used in the development of advanced wing geometries for innovative, sustainable aircraft design. But today, it's being used for football.
We have just a sting mount mounted to a turntable. We actually have a 6-component.
Wind tunnels are occasionally used in nuclear engineering, but they would actually be at this kind of low-speed stuff, because it's mainly about fluid flow modeling, heat exchanger study. So you're looking at things like a turbulent flow pattern, for instance, and its effects on your heat transfer. Mainly around optimal designs for cooling your reactor and its supporting systems. But I've never seen someone stick a reactor in a wind tunnel. That'd be a pretty big wind tunnel. But heat exchanger components, sure.
Cell here, and with this 6-component load cell we can measure all 3 components of force and torque. We then have an electric motor, right, that we can spin to basically simulate the spiral.
First, we're going to simulate one of Brady's throws where the ball travels straight into the airflow with his classic spiral.
Okay.
And everything proceeds as we expect. No significant forces or torques develop.
But during a game, a ball doesn't travel like this in a straight line.
No.
During any
There's
throw,
dynamic
its
systems.
center of mass follows a roughly parabolic trajectory.
Just like any standard projectile, bullets follow parabolic trajectories, albeit the parabola is going to be a lot flatter.
So let's say you align the ball perfectly with this parabola when you launch it. Well then, from the ball's perspective, just a moment later, this parabola
there's
starts
your
to
vector.
curve down away from the ball, which means more air will be hitting the underside of the ball than on top. Now, you would expect this would tilt the ball back, but that's only what happens if the ball is not spinning. If it is spinning, then the situation is very different, which you can see with this amazing demo.
Imagine this ring of golf balls is like a cross-sectional
golf
slice
balls.
of the football.
Nice.
Here's what happens when I try and push it back with this leaf blower. I mean, it tilts back just like you'd expect. But if I do the exact same thing, but this time get the wheel spinning,
It's got that resistance.
tilts out to the right.
And you can see why if we slow it down. So as the ring passes the leaf blower, that's where the force is applied. But each ball still has momentum in the direction of rotation. So it actually reaches its peak 90 degrees further along from where the force is applied.
Yeah, a spinning flywheel damper, but with golf balls.
And this is known as gyroscopic precession.
So
That's also why it would drift slightly sideways or curve during a long pass, which is really what you'd want in that case. You'll also get angular precession when you apply torque to a spinning reactor coolant pump shaft. And when you have reactivity spikes, when I say reactivity, just something that's going to increase the overall neutron population, you're going to have power peaking. So it's going to be a little delayed, but you're going to have some peaks. But you're also going to get, if it's due to temperature, it's going to raise temperature locally in the area, but raising temperature is actually going to lower power. It's all due to the Doppler effect. Basically the same thing of why ambulances change in pitch, why they pass you on a microscopic scale. They effectively lower the chance of causing fissions because the neutrons effectively see a smaller target. It's all probability, really, but when you're dealing with very, very large numbers like you do in a nuclear power plant, it's going to hold true.
wind was hitting it, it's going to keep the point up,
So you'd think that it would just push it back.
right?
But because it's spinning, when you push up, it actually tilts to the right.
Oh, interesting.
But it doesn't stop there. As the ball tilts right, it exposes more area on that side.
Yep.
So now, because of gyroscopic precession, the ball pitches downward. And with more air hitting the top of the ball, well, it's going to deflect to the left. And that is going to make the ball deflect back up. And now we're back to where we started. So this cycle is going to repeat. Since this is happening continuously, the nose traces out a circle around the direction of airflow. So we get a slow wobble.
We used to joke.
I love we're using technical terms like gyroscopic precession, angular momentum, and now wobble. I love it.
Whenever you would not throw a tight spiral, you would call it a tight wobbler. That was a Brett Favre coined phrase. He let it go and have a little wobble to it, and you go, oh, tight wobbler.
Now, if the ball were just traveling straight, this...
I was going to say, this is kind of like, because football players know this better than anybody. They see this all the time, but you don't necessarily need to know all of the analytics behind it in order to observe this phenomenon. So kind of like things that reactor operators see first before the engineers up in the office. Because after all, reactor operators would see effects on power before the reactor engineers do, because while the reactor engineers might have validated all of the things within, say, the simulator, some calculations based on fuel loading and stuff, there might just be some unaccounted for defects or flow anomalies. By the way, flow anomaly is a universal term for an engineer not sure what's going on. Anything involving the complex structure of a reactor. It does not surprise me that football players already had a term for something that in a 2020 study, and what Veritasium is doing in this video is just looking at basically practice working its way back to theory. It's kind of fun to see that.
Be the whole story. But remember from before, the ball's path is a parabola, meaning that from the ball's perspective, the oncoming air is constantly dipping down away from it. So the ball is trying to precess around the airflow direction, but that direction is constantly changing.
That's a beautiful illustration.
By the time the ball has reached the bottom of the precession, the airflow has moved down too. And what that means is the ball is not going to tilt out to the left as much as you'd expect. So when it precesses back up, it doesn't go as high as where it started. And over time, it is this that gradually pitches the nose of the football down, keeping it aligned with its parabolic path.
I can visualize it all, your fancy science words. I'm going all the way back to my high school days. I was a very average science student, but you're teaching me a lot.
As the ball goes through the air, there's going to be more air resistance on the bottom of the ball than on the top.
The front of the ball, not the back, because that's hitting the wind first.
The front bottom of the ball.
Okay.
And so what that means is it creates this precessive effect that pushes it out, pushes it down, pushes it right. It creates a wobble no matter what you do. So the wobble is actually not only impossible to avoid, but it's essential to make sure that the ball follows the path that you want it to follow.
Yeah. You can see this in the wind tunnel. We've tilted the ball up by 3 degrees and it's free to pivot in any direction.
Yeah, you're definitely seeing it pitch. Oh, that's awesome. What we're seeing is it's starting out aligning itself about 3 degrees off, because that's how we spin it up. But as the airflow starts,
then it goes down,
pointing itself in the direction that minimizes drag. That's so cool. I mean, that's exactly what we were expecting, but it's still incredible to see it in person.
If you look at a real football in flight, you'll notice that it spends more time angled slightly to the right when thrown by a right-hander. That is what creates the force which, through precession, gradually pitches the nose downward. It creates the turnover effect that Tom Brady was talking about.
And it's going to be more pronounced with the release imperfections for a more amateur throw, I'm sure. And it kind of goes back to no reactor core is ever perfectly symmetrical either. There is always slight asymmetry in fuel enrichment, coolant temperature gradients, and non-uniform neutron moderation. Water comes pretty close to uniform, but especially if you're using something like graphite, like an RBMK or something, moderation's going to be a lot more uneven. After all, physics is not a fan of perfection, which I'm good with. Perfection is highly overrated anyway.
The wobble is not necessarily a bad thing.
Okay, good. Peyton Manning had a good wobble on the balls, but he found a way to complete a lot of touchdowns that way.
But the rightward lean of the ball also has an unintended side effect.
Something we've heard is that for right-handed throwers, the ball will drift right, and for left-handed throwers, the ball will drift left. Do you think that's true, or is that something you notice?
So I wouldn't necessarily agree with that.
So we got Tom to throw straight down one of the lines on the field.
Is it drone set? That's a pretty straight throw.
Henry, don't move. You're making it look bad.
I'll stay planted.
The more still you go, the better it looks for my throw. It's like a catcher when you frame the pitch.
I'll frame it.
This is awesome.
From ground level, his passes looked amazingly straight. But from the drone, if you watch closely, just at the end of the pass, the ball does drift off to the right. This is because up until now, we've been ignoring a very important aerodynamic
I mean, you want to lead your runner anyway, so that's not bad necessarily.
effect, which is lift. When the ball is tilted to the right, it generates lift out in that direction. The more it's tilted, the larger this force is. The rightward tilt is required to get the ball to turn over during its parabolic path, but it does mean that right-handed throws tend to drift right. The effect is subtle, but some players notice it intuitively.
In the fall of 1991, Jerry Rice, generally considered the greatest wide receiver of all time, changed quarterbacks. In place of the right-handed Joe Montana, he was now catching passes from the left-handed Steve Young. And for Rice, something felt off. He wasn't sure exactly why, but he said the throws were coming up short. Of course, what was actually happening was that the ball was drifting away from where he expected it to be. Joe Montana's right-handed throws drifted to the right, whereas Steve Young's drifted left. It's a subtle effect.
And depending on what type of route he's running, sure.
Part of the precession that minimizes drag on the ball and lets it fly farther, faster, and more accurately.
So it's not because you're a bad quarterback throwing it with a wobble, it's because wind, you know?
Okay, so what if you're in a dome and there's no wind?
See, that's a great question. So I'm just saying this is
That's
just
a
air
great
resistance.
question.
So even in a dome, the same thing would happen.
Yeah, it would. It would just be... You'd think it'd be less of an effect, though. Especially because the wind can change direction, so it would arguably be more controlled. Because where the indoor stadium would be closer to more controlled lab conditions with more or less constant pressure, temperature, and wind. Whereas an outdoor stadium, especially if the game happens right as a front's coming in, so not just wind change, but pressure change, you can have some rain, which is going to add some unexpected moderation, not to mention affect the behavior of your receivers. Plus, even stuff like having indoor lights. Being indoor, it's probably going to be better lit than a game at night, even with outdoor stadium lights.
In an outdoor stadium or a closed-top dome, the ball will always wobble. But outdoor stadiums are significantly harder to throw in because of the wind.
Yeah.
With the ball being thrown at 50...
It's just another factor you're going to have to deal with. You're going to have to compensate for. And I would compare that to operating a reactor at steady state power versus when you're doing load follow with xenon oscillations. And xenon oscillations can be a pain because they can often take a couple of days to fully recover. And because reactor operators operate in shifts, if you had to do a down power, a key turnover brief is essential for what stage of the xenon transient you're going to be in, especially if you're still moving the reactor up or down in power. So it all just has to be covered in a reactivity turnover briefing.
50 miles per hour, most of the airflow over the ball is due to its own motion. But in winds gusting over 15 miles per hour, the weather starts to play a major role.
We commissioned the NFL data team to do an analysis of completion percentage in outdoor stadiums versus indoor domes.
One interesting thing is also in places like Colorado, for instance, where you're at a much higher elevation, air resistance is less. I know that comes into play for baseball when home run distance. It's easier to hit the ball a lot farther because of less air resistance in an outdoor stadium. You also have a better chance when playing golf of getting a hole-in-one on a par 4 or even a par 5 just by being able to hit the ball a lot farther. Though I wonder if they increase the yardage on holes in higher elevation places with lower air resistance. I don't actually know.
And they found that throws in indoor stadiums are consistently more accurate, no matter the distance.
Not
so
surprised.
maybe Brady was hard done by Foxborough, New England's stadium.
Outdoors.
Do you prefer to throw a game when it's no wind? Do you prefer wind, rain, snow? Does it matter?
I preferred outdoor, 70 degrees, humid, tiny little breeze just to keep you cool.
Right. But why did
Yeah, some of it's just how it feels on you, and if you're a person that runs hot or runs cold. I've seen this in baseball too. Like there was certain pitchers that were amazing, but only if it was 80 degrees, sunny, low humidity. But if anything was just a little off about the weather, that would mess them up. It's kind of funny.
like being outdoors as opposed to being in a dome?
I felt like my depth perception was a little better outside. I like just the natural feel of the natural air.
Yeah,
the dome always
like
felt like a vacuum.
Do you think you had an edge if the weather was bad compared to other quarterbacks?
I would say yes, and the reason why is I say I practiced in it all the time, and I think
it's important.
Getting used.
It's important to practice. That's why in nuclear power plants we run drills with bad weather, with extreme, arguably unrealistic scenarios, like all of our emergency systems failing to start. Which the odds of that are, using PRA numbers, can be in the less than 1 in a billion type failures would happen in your scenario, but you still train for them.
Conditions and the familiarity of the wind, of the humidity, of the rain, of the snow, grass field, turf field. I knew exactly what to wear for every single condition. I played 20...
Not necessarily for throws, the grass fields, but versus turf, but it's another factor that affects the whole game.
Seasons, 100 to 120 practices a year. So that's over 2,000 plus practices.
That's crazy.
The thickness you want in your sleeves. Okay, what's temperature? It's 50 degrees. Okay, this is the shirt I wear when it's 50 degrees. Oh, it's 35 degrees. This is the 2 shirts I wear when it's 35 degrees.
Yeah, you get that stuff down to a science if you practice that much.
This, the muff that I wear. This how many heat packs I put in the muff to keep my hand warm when it's 30 degrees versus 50 degrees.
You had it all dialed in.
You just have to. You just observe over time and you get better and better. It's a lot like an F1 car. Everything is just fractions of, things to do to make yourself feel the most comfortable.
There's whole sciences behind that, even with the comfort of chairs in control rooms and the ergonomics of why you put these switches here versus there. It really gets looked at for reactor operators as well. But yeah, there's a whole ergonomics, industrial engineering, time and motion studies that can be done to make that as good as possible.
So maybe Brady is a bit more scientific than he gives himself credit for. Over 300...
He just uses different terminology. I would say he's more like an engineer or an operator, which is what you'd want in a football play. Which in a way is having those skills. I could see that being good at being a football player.
3 career games, more than 7,700 completed passes, and tens of thousands of hours on the field, Brady intuitively understands all the physics we've just analyzed. Plus, he knows how to harness these effects to get the ball where he wants it to go with just a few seconds to throw it. In a game where perfection is impossible, he's internalized all the complex physics, the kinematics, the aerodynamics, and he still makes it look simple.
Yeah, I don't have to move.
So we actually made a video together with Tom Brady teaching us how to throw a football. And if you want to learn more about that, you can check it out right here.
Now we...
What is it? Baseball, golf ball, football?
For you are some balls that you've never thrown before.
Oh God, what do you guys got cooked up?
But we're not done yet.
What the heck?
In other sports, surfaces are engineered down to the smallest detail to control airflow. But footballs, they've hardly changed in decades. So we tested whether a football's design is really optimal. And to find out, we had Tom Brady throw
tennis football.
Series of custom balls, including one built to eliminate his spin entirely.
I didn't even know how you could throw that.
Now, in investigating this, we actually uncovered a secret technique that teams are using to modify their balls and give their players an advantage. But
are we bringing up Deflategate? Really?
We'll get to that in a future video, so make sure to subscribe and stay notified, and we'll see you then.
That's insane.
This video is good. I like applying nuclear engineering, science, knowledge to sports. Thanks again for the recommendation, and thanks so much for watching. I'll see you next time.